Good morning, my dear friends. I hope you all are doing great. So today I will be talking about thermochemical equation, my dear friends. What is this thermochemical equation? Have a look. If I talk about the thermochemical equation, my dear friends, here I will be taking it with respect to delta H R naught. You can also take the thermochemical equation with respect to delta H R. Yes, that is enthalpy change. But please remember, I am taking here thermochemical equation with respect to delta H R naught. That means standard. Okay, standard enthalpy change during reaction. So let's have a look. A thermochemical equation is a balanced stoichiometric chemical equation. So it has to be balanced. First thing, a thermochemical equation has to be balanced. So let us check whether it's balanced or not. Have a look here, my dear friends. If you look here, this is ethanol. And you are doing the combustion of ethanol, means you are burning the ethanol in presence of oxygen. And you are getting carbon dioxide and water, my dear friends. So in ethanol you have carbon, okay, and you have hydrogen. So if you burn the carbon, you will get carbon dioxide. If you burn the hydrogen, you will get water, correct? Now look here, let us check whether it's a stoichiometric chemical equation should be balanced. Let us check whether it's balanced or not. What is the stoichiometric coefficient here? One, number of moles. Stoichiometric coefficient I told you last time. Stoichiometric coefficient, okay, represents number of moles. So let's look here, my dear friends. If I look at the carbon, how many carbon we have? We have 2 moles of carbon, 2 into 1 is 2. And how many moles of carbon I have here? 2 moles of this carbon. That means number of carbon atoms are equal. Let's look at the hydrogen. We have 5 plus 1, 6 hydrogen. 5 plus 1, 6 hydrogen. And this side also, 3 into 2, 6 hydrogen. So hydrogen atoms are balanced. Carbon atoms are balanced. Now let us look at the oxygen. How many oxygen are here? 1. Okay. And how many are here? 6. 6 plus 1 is 7. Reactant side you have 7 oxygens. Or you can say 7 moles of oxygen atoms you have on reactant side. Product side 3 here and here 2 into 2 4. 4 and 3 is how much? 7. That means oxygen atoms are also balanced. Carbon is balanced 2 and 2. Hydrogens are 6 and they are also 6 balanced. Okay. Oxygen are here 7 and here also 7. So all the atoms are balanced. So we have a balanced stoichiometric chemical equation. So this is our balanced stoichiometric chemical equation. Let's go further. That includes the standard enthalpy change. So it includes the standard enthalpy change, that is delta H R naught. It is not necessary that we can write down only it in terms of standard enthalpy change. You can also write it in terms of enthalpy change also, my dear friends. Then you should mention here delta H R. This is also possible. Please try to understand this thing. You can write down it in terms of enthalpy change also, that is delta H R. But I am mentioning it in terms of standard enthalpy change. So I will write down naught. That's the only difference. Remember, you can take thermochemical equation in terms of delta H R, that is enthalpy change, or you can take it in terms of delta H R naught, that is standard enthalpy change. Please remember that. Now, what is the standard enthalpy change in this reaction? This is the standard enthalpy change during this reaction. Okay, we call it as standard enthalpy of a reaction. Standard enthalpy of a reaction, my dear friends. So look at this. It's a minus value. That means when you burn the ethanol, means alcohol. Okay, the burning of alcohol is a exothermic reaction. This negative sign will tell you that this is exothermic reaction, my dear friends. So please remember that. So my dear friends, you have understood now what is a thermochemical equation. It should be balanced, first thing. Okay, the number of atoms, yes, on the left side should be equal to the number of atoms on the right side, reactant side and product side. Second thing is that the enthalpy change, standard enthalpy change value, that should be also mentioned. And we have mentioned that it's an exothermic reaction. And which reaction is this? This reaction is a combustion of ethanol. So this reaction is a combustion of ethanol. So you can mention here it's a combustion reaction. And one more thing I would like to add on here, that in thermochemical equation, the physical state of reactants and products should be also mentioned. This point you should remember. In thermochemical reaction or equation we can write down. Physical states of reactants and products should also be mentioned. Now if you look at this reaction, for example, I will C2H5OH. This guy is in a liquid state, so this is the physical state of ethanol, plus 3 times oxygen. This is in gaseous state, and it gives me carbon dioxide and water, my dear friends. So 2 times carbon dioxide and 3 times water. This is in gaseous state and this is in liquid state, my dear friends. So this and this will represent the physical states. So these are the physical states of reactants and products. Physical states. This is a reactant, this is a reactant, this is product, and this is product. So what are the physical states of reactants? This reactant is liquid, this reactant is gas, this product is gas, and this product is liquid. So remember, in thermochemical equation, physical states of reactants and products should also be mentioned. And now you can look here, liquid, gas and liquid. That means physical states have also been mentioned in this chemical equation, my dear friends. So first thing, the number of atoms on reactant side and product side should be equal. Second thing, it should give us the value of delta H R naught. Yes, and that is also given. It should tell us whether reaction is endothermic or exothermic. Okay. Third thing is that it should tell us that in which state reactant is present. Whether reactant is present in the solid state, liquid state or gaseous state. And also should tell us in which state the products are present, solid, liquid or gas. So it should mention the physical state of reactants and products. And one more point also I would like to mention. It should also, I am talking about thermochemical equation. It should also mention the allotropic form of a substance also. Remember that. Allotropic form of a substance. Let me have a look. So I will write down one more point here. Thermochemical equation should mention allotropic form as well. For example, if I give you one reaction here, carbon plus oxygen gives me carbon dioxide. This is gas, and now you will usually mention this solid. Let's suppose this is solid. And we know that this is a combustion of carbon, so delta H, let's suppose under standard conditions, it will be negative, so it's an exothermic reaction. Delta H R naught is mentioned. Reaction is balanced also, 1 carbon, 2 oxygen, so balanced reaction. Physical states are also mentioned, gas, solid and gas. But let me try you one thing, man. Let me tell you one thing, that is, it is not a thermochemical reaction. Why? Because they have not mentioned the allotropic form. Allotropic form you have to mention. You know the allotropic forms of carbon, graphite and diamond. They have to mention whether this carbon is a graphite or a diamond. Yes? Then only you can take it as a thermochemical equation. Look here. Thermochemical equation should mention allotropic form as well. It should tell us that this carbon is a graphite or it is a diamond. I mentioned here physical state, it's solid. That means still it's not a complete thermochemical equation. So in place of this solid, now what I'm going to write on, have a look here. I'm mentioning here this is graphite, and graphite is an allotropic form of carbon. Then I will mention it is solid. Now it has become a thermochemical equation, my dear friends. So if any, let us suppose if you take white phosphorus, red phosphorus or black phosphorus, you have to mention in the chemical reaction that whether it's a red phosphorus, black phosphorus, yes or no, or it's a, come on, white, red or black phosphorus you have to mention, my dear friends. If you don't mention that which phosphorus is this, then your thermochemical equation is incomplete, my dear friends. So let us summarize what is a thermochemical equation. It is a balanced equation, first of all. The number of, atoms on reactant side should be equal to the number of atoms on product side, first thing. Second thing, it should give us the physical state of the reactants and products. Physical state means it should mention whether reactants are in solid state, liquid state and gaseous state. Same the products, solid, liquid or gas. Third thing, it should mention that how much of energy is absorbed or released during this process, which will be given by delta H R naught. Delta H R naught will give that. Whether it's an endothermic reaction, exothermic, that should be also mentioned. And finally, one more thing should be also mentioned, my dear friends, that if any substance is in allotropic form, let's suppose carbon is in allotropic form, and you have to mention that which allotropic form it is. Is it a graphite or it's a diamond? You have to mention that. Then only the thermochemical equation will be completed here. So I hope everybody has understood this particular thing. And remember, I have taken the value of enthalpy change in terms of standard conditions or in terms of standard states. Yes? You can take delta H R also, but I am taking delta H R naught. So the conditions will be standard here. Please remember that, make note of this. So dear friends, you have learned some facts about the thermochemical equation, my dear friends. Now let us come up with some conventions regarding thermochemical equation. It's a very easy thing. The stoichiometric coefficients in thermochemical equation represent number of moles, my dear friends. Let us suppose if I take N2 plus 3 times H2 gives me 2 times NH3. This is the formation of ammonia. Now look here, this 1 and this 3, they are the stoichiometric coefficients of reactants, and they will give me the number of moles of reactants. And this 2 is basically the stoichiometric coefficient of products. So it will give me the number of moles of products. This will tell me that we are taking 1 mole of nitrogen, and this stoichiometric coefficient will tell me that we are taking 3 moles of hydrogen. So 1 mole of nitrogen reacts with 3 moles of hydrogen, and I am getting 2 moles of NH3. So I hope you have understood the first term. Let us come to the second term. Delta H R naught value tells us whether the reaction is exothermic or endothermic. If it is exothermic, it will be negative. If it is endothermic, it will be positive. So have a look here, my dear friends. If you look at this reaction, it's a negative value. So delta H is negative, so it's exo. And here delta H R naught is positive, so it is endo. So second point also you have understood, and remember its unit is kilojoule per mole. So look here, kilojoule per mole, kilojoule per mole. That means it's measured in kilojoule per mole, correct? Let's look at the last point now. When reaction is reversed, if you reverse a particular reaction, the sign of delta H R naught also reverses. Yes? That means if forward reaction is exothermic, the backward reaction will be endothermic. Remember. Look here, my dear friends. If forward reaction is endothermic, then backward reaction will be exothermic, and vice versa, which means if the forward reaction is exothermic, backward will be endo. If forward is endo, backward will be exo. So the signs will change. Plus will change to minus and minus will change to plus. Let's have a look. The first reaction, if you take here, it's a formation of ammonia. And you can see here, it's an exothermic reaction. But now in second reaction, if you see, I am taking reverse of it. What is the reverse? Ammonia should give me N2 and H2. This is the reverse. This is the reverse reaction. Now this is your reactant and these are your products. You can see the arrow. So I am taking the same thing. Ammonia breaks into nitrogen gas and hydrogen gas. That is here. Ammonia breaks into nitrogen gas and hydrogen gas. That is a reverse reaction. So the forward reaction, my dear friends, was exo. So the backward reaction means conversion of ammonia back into N2 and H2. So ammonia will change into N2 and H2. The reverse of this. The sign will also change. Exo will become endo. So remember this important point. For any chemical reaction, if forward reaction is exo, the backward will be endo, and vice versa, my dear friends. I hope you have understood these conventions and all. Please make note of this particular thing. Dear friends, let us take one question now. Okay, so we have taken one thermochemical equation here, my dear friends. So here we have iron oxide is made to react with hydrogen gas. So obviously what happens, these oxygen atoms will come out and they will interact with the hydrogen and will make water. And iron oxide will be reduced into iron, because iron oxide is basically losing the oxygen. So loss of oxygen is reduction. So we are getting iron here. So now what is my point here? In this chemical reaction, they have told us calculate. They have told us calculate delta H R naught for this particular chemical reaction. But in order to calculate this delta H R naught, okay, first of all, we should see that what is given to us. Have a look here. These things are given to us. You can just have a look. That standard enthalpy of formation for water and standard enthalpy of formation for iron oxide, for hydrogen and for iron. Everything is given to us. Okay. Now we have to simply write down an expression here, my dear friends. So I have already told you, in order to calculate delta H R naught, last time I told you we have to take the sum of the standard enthalpies of products multiplied by the stoichiometric coefficients. That's number of moles. Okay, my dear friends, minus sum of the standard enthalpy. So it should be mentioned here as delta H F naught, my dear friend. Delta H F naught. So here also delta H F naught. So standard enthalpies of reactants, my dear friends. So that was the expression which I have written last time, my dear friends. Now let us elaborate it. So let's take the sum of the standard enthalpies of products first. So if I take the sum, these are my products and these are my reactants. So what is my expression here, my dear friends? Have a look. Let's take the product first. So here the number of moles of products are here. That is AI is here 2. So I will take 2. Then I will take the delta HF naught for product. My first product is iron, and iron is basically in solid state. And there is one more product, that is water. So how many moles? 3. That means AI is here 3. So I will write down 3 moles. Then I have delta HF naught. Then we have here water, and water is basically in the liquid state, my dear friends. So this is all about products. Then I will go for reactants. So minus So reactants are here Fe2O3 and 3 times H2. So my dear friends, I will mention here. We have here Fe2O3, that's one time only. So here Bi is nothing but one time. That is delta H F0 Fe2O3. That's in solid state. Plus one more reactant is there, 3 times delta H F0. Okay. Then we have hydrogen. That is basically in the gaseous state. So remember, my dear friends, this is our expression. Let us put the values now, my dear friends. So if we try to put the values, you have a look. So 2 into delta H F0 for iron. So look here, when iron is basically in solid state, it's the pure form. It's just an elemental, iron. And the delta H F0 for this, the pure form of iron or elemental iron is 0. Even for this, elemental hydrogen, the standard enthalpy of formation is 0 as far as convention is concerned. So remember, for hydrogen gas, even for iron solid, and we will learn also for bromine liquid, even the table is basically given in your NCERT book, you will understand. So enthalpy of formation for hydrogen element and for iron element in their pure form is basically 0. So for iron, I will mention here 0 plus 3 moles we have here. Okay, so enthalpy, standard enthalpy of formation for water, that is given to me, that is minus 285.83 minus 285.83 multiplied by 3 moles here minus, now look at the iron oxide. If you look at iron oxide, it is minus 824.2. So we have only 1 mole here, so we'll write down here minus 824.2. That's for iron oxide. Now you know for hydrogen that is 0 only, correct? So I will write down plus 3 into 0. So my dear friends, now this will be 0 here and this factor is also 0. Then minus into minus will be plus, but this factor will be minus. So you have to multiply these two things, okay? And here we will have a plus factor and here we will have a minus factor, my dear friends. So finally, my dear friends, okay, your value will come out to be minus 33.3 kilojoules per mole. You can just calculate this particular thing and your value should come out to be minus 33.3 kilojoules per mole. That means this reaction is basically exothermic. So this value, this question mark is now minus 33.3 kilojoules per mole. Okay? So remember, my dear friends, how many moles of iron are formed in this reaction? You are making 2 moles of iron. So in this reaction we are making 2 moles of iron. So for the formation of 2 moles of iron, how much of energy is released? Minus 33.3 kilojoules. If I tell you one more thing, our question is done, we got the value. But if I tell you one more important point, for the formation of 2 moles of iron in this reaction, the energy released is minus 33.3 kilojoules. If I tell you that for the formation of 1 mole of iron, what will be the energy released? Half of this. For the formation of 4 moles of iron, how much of energy will be released? Double this amount. Are you following my point or not? This reaction is basically for the formation of 2 moles of iron are formed. And we are getting this much of energy. But if we make 4 moles of iron, then we will get double. But if we make 1 mole of iron, then half of this. So 33.3 divided by 2. Yes? But if we make 4 moles of iron, then 33.3 multiplied by 2, it will be doubled. So that is the relationship here. So I hope you have understood that how to calculate this particular thing, that is delta H R0 for this reaction. Please make note of this. So dear friends, let us talk about now Hess's law of constant heat summation. What is this all about? Have a look. Hess's law states that the standard enthalpy change for the formation of any compound A. Let us suppose you are making any compound A. In how many steps? In one step. Okay? So how much will be the enthalpy change for the formation of any compound A in one step is equal to the sum of the standard enthalpy change for the formation of same compound A in multiple steps. Very simple it is. Let us suppose you make any compound A in one step and some energy change will happen. Some standard enthalpy change will happen in that one step. And how much enthalpy change or standard enthalpy change is happening for the formation of any compound A in one step. The same amount of change will happen when the same compound is formed in multiple steps. Let us try to understand it by an example. Let us suppose if I take the first step formation of carbonic acid, let us call this carbonic acid as our compound A. So here we are making the carbon dioxide in just one step, my dear friends. So we took carbon, graphite, allotropic form of carbon, and I made it to interact with oxygen and I got carbon dioxide. Now this is the one step formation of carbon dioxide and this is the enthalpy change. So my dear friends, Hess's law states that the standard enthalpy change for the formation of any compound A in one step. So that means I will write it like this, delta H R naught, okay, for the formation. Let us suppose this is the formation of carbon dioxide in one step. So this is for carbon dioxide, or I can also mention it, this is for the formation of carbon dioxide in one step. So this carbon dioxide is just your compound A. So this is the standard enthalpy change for the formation of carbon dioxide in one step, and it will be equal to, have a look here, the sum of the standard enthalpy change for the formation of same compound A in multiple steps. Who is the compound A? Carbon dioxide. You are making it in one step and that is your delta H R naught. That is the standard enthalpy change for the formation of what? Carbon dioxide in one step. Now I will make the same carbon dioxide, but I will make it now in two steps. Two steps here means multiple steps. So look here, multiple step formation of carbon dioxide. So have a look. In step number 1, we are burning the graphite in less amount of oxygen, insufficient amount of oxygen, and I am getting carbon monoxide. Yes? So then this carbon monoxide I am taking in step number 2 and further burning it, and I am getting carbon dioxide. And this is my compound A, my dear friends. Here the compound A was formed in two steps. We call them as multiple steps. And here the compound A, this is our compound A. This compound A was formed in just one step. And this is the energy change right out here. And here the same carbon dioxide, the compound A, was formed in multiple steps. It was formed in two steps. First of all, carbon was converted into carbon monoxide. Then carbon monoxide was converted into carbon dioxide. And as far as the statement of Hess's law is concerned, how much is the standard enthalpy change for the formation of any compound A in one step? Will be equal to the sum of, the standard enthalpy change for the formation of same compound A in multiple steps. So this is a one step formation of carbon dioxide, and it will be equal to the sum of standard enthalpy change. So it will be equal to the sum. I am taking this sum here plus the standard enthalpy change, okay, for the formation of same compound A. Who is that? Carbon dioxide in multiple steps. So let's take on the first one here. That is your delta H R1, okay, naught, then delta H R naught 2. So my dear friends, now this is the multiple, these two will give the multiple step formation of carbon dioxide. So one step formation of carbon dioxide will be equal to the sum of the enthalpy change or standard enthalpy change in multiple steps. So this value and these two values should be same. Yes or no, my dear friends? And we know what is the value right out here for this. Let us fix up this value and this values, and they should be equal. That means LHS should be equal to RHS. One step formation of carbon dioxide, okay, and multiple step formation of carbon dioxide, the energy values should be equal. Yes, that means whether you are making carbon dioxide in one step or in many steps, the energy change has to be same. LHS has to be equal to RHS, my dear friends. Please make note of this, and I will fix up these values into this. Please make note of this. So dear friends, let us fix up the values now here. Delta H R naught, formation of carbon dioxide in one step. So that is minus 393.5. This is minus 393.5. So minus 393.5. Okay. So here, this is basically the multiple step formation of carbon dioxide. So in first one, delta H R1 naught is 110.5. It's equal to minus 110.5. Okay. And then after that, there is another factor, delta H R naught 2, that is minus 283. So first of all, I have to take their sum here. So it is minus 283. This represents formation of CO2 in one step. Okay, and these two will represent formation of CO2 in multiple steps. So now, if you take it as plus minus minus, so both will be minus here, so you have to do the addition of them. This has to be equal to this. So my dear friends, here minus 393.5 is equal to minus 393.5. That means LHS is equal to RHS. And obviously the units are kilojoule per mole. Whether you are making carbon dioxide in one step or you make the carbon dioxide in multiple steps. How much is the standard enthalpy change in one step for the formation of carbon dioxide? Same will be the enthalpy change in the formation of carbon dioxide in multiple steps. Okay, so please remember that particular thing, and it's about Hess's law, my dear friends. It's not necessary that it should take place only in two steps. It can take place in multiple steps like 3, 4, 5, 6. But some of the enthalpies of multiple steps should be equal to the enthalpy change for the formation of a compound in single step. Remember that particular thing. With this, would like to end today's session. Have a great time. Thank you.